All right, before I was cut off, because these videos can only be 15 minutes long, we were talking about electrolytes and non-electrolytes. Now, electrolytes are the soluble ionic compounds, the 7 strong acids, as well as the weak acids and bases. Now, this is how you construct a dissociation equation. You just set it up to look like a balanced chemical equation. It just, instead of showing a reaction, you're simply showing a physical change, just the dissolving of the salt, in this case, into ions. Now, when you write it all out and balance it, this one works with just coefficients of 1, but when you write it out with the 2s and 3s and such, just remember, the more ions that are produced, the stronger the electrolyte is. Also, a thing to remember when you construct these, let's say this was sodium sulfate instead of sodium chloride. If there's a polyatomic ion, you don't bust up the ion. Like sulfate would just be left as SO4, 2 negative. You don't try to bust apart the sulfur and the oxygen because they stay together, and when the substance dissolves in water, you'll just have 2 ions, the positive and the negative. All right, so weak versus strong again in terms of how you set up the equations for them. The strong electrolyte is going to be producing more ions because it completely dissolves. It's 100% disassociated. So you draw that with a regular arrow and voila. Now, this is nitrous acid. Nitric acid is strong, but nitrous is weak. So for that reason, you draw out the products the same. You show the ions it's going to bust up into, but you draw an arrow going both directions, because in water, in an aqueous solution, both of these are happening. So while some of the nitrous is being split apart into nitrite and hydrogen ions, some of it's also reforming back into the original substance, hence the 2 arrows. And that's why it's only weak, because what's happening in the water is some of it's split up and some of it is still together. All right, so it's not completely dissociated if it's weak, so you need the 2 arrows, or a double-sided arrow. Now, sample exercises. Classify these ionic compounds as soluble or insoluble. Well, sodium carbonate. Now, there's a rule for carbonate, but that's not where my brain goes first with this. It has sodium in it. Sodium is group 1, and anything with a group 1 metal is always soluble. So sodium carbonate is soluble in water. Now lead sulfates. Okay, remember lead is one of those that is not soluble. Let's see if I have the answers in here. Nope, I don't. All right, so lead sulfate would be insoluble according to our solubility rules. All right, for the rest, the other practice exercise we have here, cobalt hydroxide. Okay? The rule for hydroxide is that they're insoluble unless it's a group 1 metal or the bottom of group 2. Well, cobalt is a transition element. It's not in group 1 or group 2. So this would be insoluble. It will not dissolve in water. All right, the next one, barium nitrate. A lot of the barium compounds aren't soluble, but nitrates, that was our first rule on our solubility rules, nitrates are always soluble. Ammonium phosphate. Ammonium, remember, is to be treated like he's in group 1, NH4+, and ammonium and group 1 compounds are always soluble. All right, now it's time to predict the identity of a precipitate that forms when you mix together these 2 compounds, barium chloride and potassium sulfate. And we're supposed to write the balanced chemical equation for the reaction. Try that on your own. I can't do that on here. The barium chloride, you need to figure out whether that's soluble in water. If it is soluble in water, you would put AQ parentheses after it. And it is soluble because chlorides are soluble except for with silver, mercury, and lead. The potassium sulfate is soluble because potassium's in group 1, so I'll put AQ after it. For the products, this is just an exchange reaction or a double replacement reaction, whatever you want to call it. So the metals are going to switch places. The potassium is going to pair up with the chlorine. That will also still be soluble because anything with potassium, group 1, is soluble. Now my other product, barium sulfate, that's another story. Okay, barium sulfate is not soluble. So instead of putting a Q after it, I'm going to put an S in parentheses. That is the precipitate. A precipitate is simply something that forms from the reaction of two soluble substances. It's a solid that does not dissolve in the water. So the lab we did the other day with figuring out the identity of an unknown carbonate, that formed a precipitate, the calcium carbonate that you filtered out. The calcium carbonate wasn't soluble in that example. So we'll do these in class. All right, just some more questions. What dissolved species are present in a solution of KCN? Potassium cyanide. Okay, well, we don't have a rule for cyanide, but we do have a rule for potassium. It's in group 1, so it's soluble. Okay, what is actually going to be floating around in the water in this instance? It's not going to be number 1 because it's going to dissociate completely in water because it's soluble. And here it's together, so that's not what actually happens. In number 4 down here, we split up the polyatomic ion, and that's a no-no. Okay, the polyatomic ions stay together. Okay, so that narrows it down to 2 and 3. If you remember that metals are positive, you know number 3 can't happen. The potassium's floating around with a positive charge, and the cyanide is floating around with a negative charge. That's what actually would be in the water at this point, number 2. All right, now for the next one, the sodium perchlorate. Once again, it's a group 1 metal, sodium is, so this will be soluble in water. So number 1's out. Now the question is, what in the world do we do with this perchlorate ion here? Well, we leave it put together. We don't bust it apart. Okay, the perchlorate ion is ClO4 with a -1 charge. We leave it alone. Okay, so I'm not even sure what's going on with that one. So number 4 would be the right answer. You just leave the ClO4 negative together as just one ion. So number 4 is what this would look like dissolved in water. All right, now another sample question. Which solute will cause the light bulb in the experiment shown in 4.2, the picture we saw with the differing brightnesses of the light bulbs? Which one would cause the light bulb to glow more brightly? CH3OH or MgBr2? Okay, this is actually methanol. It's an organic compound, and then versus magnesium bromide. Okay, cannot determine without concentration information. No, we definitely can figure this out, and it won't be with equal brightnesses. Why? Because right here, the magnesium bromide, that is an ionic compound, and it is soluble. Bromides are soluble except for with silver, mercury, and lead. So that is a strong electrolyte. We will get a brightly lit light bulb out of this. This guy is not a hydroxide. I know you might see that OH and think so, but it's not, because this CH3 is not a metal. Those are non-metals. So this is actually a covalent compound. H can act like a metal or a non-metal, I realize, but in this instant with the carbon, this is actually an organic compound. It's an alcohol, methanol. So that being the case, it is not going to produce a brightly lit light bulb like this ionic compound is. The ionic compound is going to, I guess, win, so to speak, and we will have a strong electrolyte. All right, which of the following is a strong acid? Once again, that has nothing to do with the concentration. A strong acid, whether it's 1 molar or 12 molar, is going to completely disassociate in water, and that's what makes it a strong acid. So which one of these is it? Sulfuric acid, H2SO3, hydrobromic acid, or acetic acid? Well, only one of these is one of our 7 strong acids, and that's the HBr. HCl, HBr, and HI All the halogens except for F are strong acids. HF is a weak acid. So if it's not one of those 7 strongs, it's weak. This HC2H3O2, it's a lot to say, that is the acetate ion. So this is acetic acid. This is the acid found in vinegar. And it is a very, I guess, popular weak acid to use in examples. So get used to seeing acetic acid. And let's see, I'm trying to decide if I want to stop or not. Okay, so what we did in that earlier example was just simply a double replacement reaction when ions of 2 separate compounds exchanged places in water in an aqueous solution to form 2 new compounds. Double replacement reactions like this one tend to happen in water. So in a double replacement reaction, you're going to form certain things. It's either going to make a solid, a precipitate, or an insoluble gas that's going to bubble, or some kind of molecular compound, usually water. And so these double replacement reactions can be acid-base reactions, or they can be precipitation reactions. If it's an acid-base reaction, you're going to form water. There's your molecular compound, and sometimes you'll even get bubbles. You'll get little carbon dioxide bubbles or something. All right, so here's what a precipitation reaction looks like. You're mixing what appears to be 2 different beakers of water, but what's actually happening is there's some kind of soluble, probably some lead nitrate in here, and then another soluble substance floating around in here. Trying to think, like some sodium chloride, just some table salt. And they dissolve in water and are invisible, but when you mix them together, that lead finds the chlorine and you end up with like a lead chloride precipitate. How do you know what the precipitate is? That's why you need to have your solubility rules memorized. Another word for these reactions are either metathesis or exchange reactions. Metathesis means to transpose. Basically, the metals are just switching places. The potassium's now going to be combined with the nitrate, and the silver's now going to be with chlorine over here. The potassium nitrate is soluble in water, and so it's still going to get the AQ written after it. The silver chloride, though, chlorides are soluble except for silver, mercury, and lead. So this would be a solid precipitate that would form. Now, so exchange, transpose, metathesis, just double displacement, double replacement, these are all words for this type of reaction. So you can see who's switching places here a little bit better. Now, what actually happens when you put these chemicals in water? Trying to show you visually what actually happens with these ions. So the silver nitrate and the sodium chloride start out combined in an ionic solid, but then they're both soluble in water, and so they separate and float around. But once the silver and the chlorine bump into each other in the solution, they are going to stick together so well that water cannot pull them apart. The silver chloride is not soluble, so it will be our precipitate. And it'll sink to the bottom, and the sodium and the nitrate are going to continue floating around doing nothing. So here it is on a larger scale. All the AGs and the CLs are going to combine and collect at the bottom of the beaker here as a white solid, and the sodium and the nitrates will continue to float around. They're called spectator ions for that reason. They're like spectators at a football game. They're just sitting in the crowds cheering, but they're not really part of the game, and that's what the sodium and the nitrate are doing in this example. Okay. Now at the end, if I added stoichiometrically equivalent amounts of the silver nitrate and the sodium chloride, at the end, all the silver and all the chlorine would be in a precipitate, while the sodium and the nitrate would continue to float around in the water, being spectators. Ta-da! All right, I'm going to pause here.